Hello my friends and welcome back to the You Can Do TV channel. We're in Otto Klosterman's facility that processes large, thick, and long steel components using some of the most advanced cutting and cold forming technologies available. The facility boasts the largest bending press in Europe, exerting a force of 4,000 tons and referred to as the Giant by the workforce. With a total of 8 different bending presses, the machinery can handle materials ranging from structural steel, light metal, and stainless steel to high-strength steel grades. These presses can cold forge components up to 20,000 millimeters long and thick, a testament to their power and precision. The company's clientele spans bridge, ship, and crane builders, as well as heavy engineering and offshore equipment companies. Otto Klosterman also produces complex parts for wind farm tripod foundations in the North and Baltic Seas, a task that few companies can undertake. In the realm of steel cutting, the facility employs cutting-edge micro-beam plasma technology. This equipment, equipped with 5 chamfering tools and 390 degrees burner heads, can create complex chamfers with swivel angles from -45 degrees to +45 degrees. The systems can produce intricate flame cuts and weld seam preparations, eliminating the need for costly post-processing. Prefabricated components are stored efficiently in a large warehouse or a 9,000 square meters outdoor storage area. Klingelnberg's gear production process follows lean production and lean management principles, ensuring efficiency and precision. The use of high-quality raw materials meeting defined standards is fundamental. Gear manufacturing involves fully automated tool settings based on Chemo's calculations, enabling precise machining. The process follows a consistent closed-loop approach for continuous quality control. Expertise in metallurgy and advanced testing methods, such as contact pattern inspection and grinding burn checks, ensure superior component quality. Klingelnberg economically grinds bevel gears up to 1,100 millimeters while maintaining strict quality assurance standards. Turkey's stainless steel kitchenware industry has experienced significant growth, establishing itself as a key player in the global market. The country's strategic location, coupled with a robust steel production infrastructure, has facilitated this development. In 2023, Turkey's steel exports reached $14.9 billion, accounting for 6.7% of the nation's total exports. This robust export performance underscores the industry's global competitiveness. The stainless steel kitchenware sector benefits from the presence of major global players which have established operations in Turkey through joint ventures or acquisitions. These companies produce a wide range of products, including cutlery, pots, and pans, adhering to international quality standards. Government initiatives have played a pivotal role in supporting the industry. Policies aimed at enhancing competitiveness include financial support for technological advancements and innovation, as well as incentives and tax breaks to promote exports. The Ministry of Trade collaborates with industry associations to organize trade fairs and events, further promoting Turkish stainless steel products in international markets. Looking ahead, the industry is poised for continued growth, driven by rising domestic and international demand for high-quality, durable kitchenware. Advancements in technology, such as smart kitchen appliances and eco-friendly materials, are expected to further boost market expansion. Additionally, A growing awareness of health and hygiene is increasing the preference for stainless steel kitchenware among consumers in Turkey. The production of a Torino alloy rim wire wheel involves several precise stages. Cutting and shaping the rim. The process begins by cutting a 5 meters thick walled 5000 series aluminum tube to the correct length using a band saw. The rough edges are then smoothed on a lathe to prevent cracks in subsequent operations. The tube is pressed using a 200-ton press and a custom-designed plug, shaping it to the desired form. The tube is then mounted on a spinning machine at Sapphire Spinning Limited, where it is gradually shaped through multiple passes, ensuring it matches the exact specifications. Fine-tuning the shape. After spinning, the wheel is further shaped on a large rim lathe. This fine-tuning adjusts the thickness at various points, tailored to the wheel's application and design. Polishing. For a polished finish, the wheel undergoes a multi-step sanding and polishing process. Starting with coarse grits, it is worked down to finer grades, revealing a mirror-like shine through craftsmanship. Marking and drilling. The wheel is marked for spoke alignment, and dimples are pressed to ensure accurate spoke nipple seating. The center is drilled, and holes are precision drilled for spokes, ensuring the correct angle for each row. Wheel assembly. Spokes are cut, bent, and threaded, then inserted row by row into the rim. The wheel is tensioned, trued, and checked for proper alignment. After inspection, the wheel is stamped, packaged, and prepared for dispatch. The alloy wheel production industry in India has experienced significant growth, driven by rising automobile sales and increasing consumer demand for premium vehicle features. As of 2024, the Indian alloy wheel market is valued at approximately $1.5 billion and is expected to grow at a CAGR of 8 to 10% over the next 5 years. This growth is fueled by expanding passenger and commercial vehicle segments, as well as the increasing adoption of lightweight and fuel-efficient materials. India produces over 15 million alloy wheels annually, with major players dominating the market. Domestic demand is projected to rise due to the government's focus on Make in India initiatives and increasing local manufacturing. Additionally, the export market is expanding, with Indian manufacturers supplying alloy wheels to key international markets, including the United States, Europe, and Southeast Asia, enhancing the industry's global footprint. The DMS Revolution CNC metal spinning lathe shapes a solid brass lamp top by rotating the brass blank at high speed. Using precise CNC control, a forming tool applies pressure, gradually shaping the brass into the desired lamp top design with accuracy. Aerospace aluminum machining tools, the Aero ETS and Aero EXTL series, are specialized aluminum machining tools designed for the aerospace industry. These tools provide high-speed, precise roughing and finishing of aluminum A7075, a material commonly used in aircraft manufacturing. The Aero ETS tool, $25 XR3, achieves a material removal rate, MRR, of 4,050 cc per minute with a spindle speed of 18,000 minutes and a feed rate of 16,200 mm per minute, offering efficient roughing operations. The Aero EXTL tool, $20 XR3, is optimized for finishing, operating at 14,300 minutes with a feed rate of 6,435 mm per minute, ensuring smooth surface finishes. Additionally, the Slot 972 solid carbide cutter provides precise slotting, operating at 10,900 minutes with a feed rate of 4,905 mm per minute, enhancing productivity in aerospace applications. The steel wire manufacturing process begins with raw steel rods undergoing descaling to remove impurities. The rods are then drawn through a series of dies to achieve the desired diameter. For galvanized wires, the drawn wire is coated with zinc to enhance corrosion resistance. Quality checks, including UTS and resistivity testing, ensure durability and compliance with industry standards. AMNS Culvert's Hot Roll Mill in Alabama is a state-of-the-art facility producing high-quality steel through advanced hot rolling processes. It supplies industries like automotive and construction, offering superior surface quality, strength, and precision in rolled steel products. The installation of the Becker-Mewis duct twisted on the 7,100 TEU container vessel Santa Rita in Rotterdam involved several precise steps to ensure optimal performance and energy savings. The process began with a 3D scan of the vessel's geometry to customize the fin's shape. This was followed by fin preparation, adjustment, and accurate positioning. Quality control included IR scanning for preheating temperature, magnetic particle testing, and ultrasonic testing to ensure structural integrity. The retrofit achieved a 3% energy saving, enhancing the vessel's fuel efficiency. Aluminum billet production from scrap involves collecting and sorting aluminum waste, which is then cleaned to remove impurities. The scrap is melted in a furnace at around 660 degrees Celsius, cast into molds to form billets, and cooled. These billets are later homogenized to enhance their mechanical properties for further processing. The Toyota Previa, once a reliable vehicle that traveled thousands of miles, met its end at the metal recycler. Now crushed and repurposed, it likely lives on as aluminum cans, a refrigerator, or other everyday items, continuing its journey in new forms. Metalli Stampati Cavaletto specializes in producing brass fittings through precision hot forging, machining, and finishing processes, ensuring high-quality, durable components for various industrial applications. The hot strip rolling process starts with receiving and storing slabs from continuous casting or conditioning. Slabs are reheated to 1,200 degrees Celsius, descaled, and rolled through multiple passes to the desired thickness. After edge trimming, they are coiled, cooled, inspected, and prepared for dispatch. Automotive alternators are essential for generating electrical power in vehicles, converting mechanical energy into electricity. Typically, modern automotive alternators produce 13.5 to 14.8 volts to charge the battery and power electrical systems. They usually generate 50 to 150 amps, with high-performance models reaching 250 amps for vehicles with advanced electronics. Efficient alternators improve fuel economy and reduce emissions. Global demand is rising, with the automotive alternator market expected to reach $32.4 billion by 2030, driven by electric and hybrid vehicles. Licor Menage frying pans are manufactured in Bergara, Gipuzkoa, Spain, using 18/10 stainless steel and 99.5% aluminum. The process includes deep drawing, sandblasting, applying a PTFE non-stick coating, painting, and riveting. Available in diameters from 12 to 40 centimeters, these pans ensure quality and durability for everyday use. Open die forging at this factory is the only process in Switzerland offering open die forging, ring rolling, closed die forging, and complete machining under one roof. This enables unique solutions for high-quality individual and small series parts. The programmable 3,000-ton press ensures efficiency, reproducibility, and versatility for workpieces weighing 2 to 4,000 kilograms. The forging process of a locomotive chassis part, approximately 100 kilograms of steel, involves rough shaping with a pneumatic hammer, 900 kilojoules, 1959, and further forming with an electro-hydraulic die hammer, 1,250 kilojoules, 2003. The work requires 3 heating cycles, 1,200 degrees Celsius, and over 100 blows, completed with trimming presses. The casting process involves shaping molten metal by pouring it into molds, allowing it to solidify. Eisengießerei Metzger, headquartered in Kalnach, Switzerland, produces 2,500 metric tons of cast parts annually. Advanced 3D printing from X1 enhances efficiency by enabling complex hybrid molds and sustainable sand recycling. This innovation allows for high-precision components with minimal post-processing, combining modern and conventional methods. Voxeljet's 3D printing technology enables the production of complex plastic parts for investment casting. This powder-based process involves applying PMMA powder in 100 to 150 micrometer layers while a print head selectively deposits a binder to form the model. After printing, models harden in the build box before being unpacked and cleaned. The plastic parts are sealed with wax for smooth surfaces and can be used like traditional wax models. This method allows for precise, cost-effective manufacturing of intricate components, including large parts up to 1 meter in length. The Linsinger KSS 1600 uses a unique 3-point clamping system to securely hold bent billets, cutting efficiently with line-cut and brazed saw blades, ensuring smooth chip flow for continuous 3-shift operation. The production process involves advanced in-house design and manufacturing of hydraulic valves, valve blocks, and related components. Utilizing state-of-the-art tools, automated systems, and rigorous testing, products are customized to meet customer needs while ensuring quality, precision, and efficiency. The ring mill ERM 900 is a multi-stage ring mill that enables continuous production of complex cross-sectional forged products. It streamlines the manufacturing process by performing multiple forming stages in sequence, improving efficiency and precision. After scrap gold is sold, it undergoes a melting process to be recycled. The gold is first cleaned to remove impurities, then heated in a furnace at around 1064 degrees Celsius, 1947 degrees Fahrenheit, until it liquefies. Once melted, it is poured into molds to form bars or ingots. The refined gold is then reused for jewelry, electronics, or investment. Manufacturing of round link chains. The production of round link chains involves several precise processes to ensure durability and strength. It begins with selecting high-quality steel wire, which is cut to the required length. The wire is then formed into individual links using specialized bending machines. After shaping, the chain links are welded using advanced flash butt welding to create a strong, seamless joint. Post-welding, the chains undergo heat treatment to enhance their mechanical properties, including hardness and tensile strength. Forging of components. Forging involves heating metal billets and shaping them under high pressure to produce strong, durable components. This process is essential for creating load-bearing parts with superior mechanical properties. Bending and welding of master link. Master links are formed by bending thick steel rods into the desired oval or circular shape. After bending, the joint is flash butt welded and then heat treated to ensure high strength and resistance to fatigue. The Fichin 4 Rolls plate rolling machine with Wind Tower's automation system is a highly advanced piece of equipment designed for efficient and precise plate rolling. Central to its functionality is the side support with a clamping system, ensuring the plate remains securely in place during the rolling process, providing stability and precision. Additionally, the top support for conical sections allows for the rolling of conical shapes, adding versatility to the machine's capabilities. Equipped with numeric control for plate rolling automation, the machine uses a CNC system to automate the rolling process, ensuring high precision and repeatability. The motorized feeding table with automatic alignment feeds the plate into the rolling machine and automatically aligns it, reducing the need for manual adjustments and increasing efficiency. This CNC-controlled plate feeding and automated plate alignment system ensures consistent positioning and minimizes errors. High plate pinching power is another key feature, allowing the machine to exert significant force to pinch the plate securely, enabling precise pre-bending and rolling. This, combined with the machine's ability to perform powerful pre-bending with extra small flat parts, reduces the need for additional re-rolling and enhances the quality of the finished product. The rolling process is highly accurate, resulting in uniformly bent plates with minimal deviation, thanks to the precise plate bending capabilities. The machine also features secure side support action, ensuring that the plate remains stable throughout the rolling process, thereby reducing the risk of deformation or misalignment. The automation system minimizes operator involvement, allowing for faster and more consistent production. One notable feature is the precise plate edge alignment before tack welding, ensuring accurate and secure welds. Faster production is achieved through the machine's design, which allows for simultaneous movements such as rolling and feeding, thus reducing overall rolling time and increasing productivity. The machine can prepare the next plate for rolling while the current plate is being tack welded, further speeding up the production process. Tack welding can be performed while the plate is still in the machine, saving time and ensuring proper alignment. Once the rolling and welding processes are complete, the finished rolled can is unloaded, ready for the next production step. The cylindrical block and flange fitting process for wind towers or pressure vessels using a flange fitting station and an overhead crane represents a significant advancement in industrial manufacturing. This innovative approach provides numerous advantages over traditional methods, including enhanced efficiency, safety, and quality. Traditionally, the process of cylindrical block and flange fitting to wind tower sections or pressure vessels involves multiple steps that require considerable use of overhead cranes. The standard procedure typically includes flipping the cylindrical shell to a horizontal fitting table for flange fitting, performing the necessary fitting and welding of the flange, and then flipping the shell back to its original vertical position for final welding and assembly. This method demands extensive crane operations, which not only lengthens the work cycle but also increases the risk of workplace injuries and potential damage to the components. The flange fitting station streamlines this process by eliminating the need to flip the shells, thus significantly reducing reliance on overhead cranes. The work cycle is drastically shortened. For example, in offshore structures, the work cycle can be reduced from 8 hours to just 2 hours. This substantial time saving enhances overall productivity and allows for quicker project completion. The elimination of shell flipping minimizes the chances of injuries associated with crane operations. The traditional method involves considerable risk due to the need for lifting and turning heavy components. By contrast, the flange fitting station ensures 100% increased safety by keeping the shells in a stable position throughout the fitting and welding process. The leveling tolerance of the flange is achieved without the need for additional machining, which is often required in traditional methods to correct misalignments caused by multiple handling steps. This results in better alignment and a more precise fit, contributing to higher overall quality of the final product. The continuously growing size of wind turbines necessitates larger diameters and heavier weights for flanges and tower sections. Handling these large components with overhead cranes becomes increasingly challenging and requires specialized skills and tools. The flange fitting station addresses these challenges by allowing flange fitting without turning the shell, thus freeing up overhead cranes for other essential tasks. Additionally, the reduction in the use of lifting clamps further minimizes the potential for component damage, reducing the need for repairs and rework. The Jutec Bending System 3000 is a highly efficient, mobile bending machine designed for precision and repeatability, whether used in a stationary position or directly at the installation site. Its compact construction allows for easy transport and setup, facilitated by solid transport cases. The system's powerful motor and precision gear ensure a robust drive, while position detection on the bending axis guarantees optimal bending accuracy. Setting the bending angle is straightforward with the set actual value display. The Jutec Bending System 5000, on the other hand, is an economical solution for achieving tight bending radii. For installations, the tripod and the principle of a stationary tube with a rotating tool allow bending with minimal space requirements. The use of slide shoes for thin-walled tubes ensures wrinkle-free bending, making it ideal for creating arcs with minimal deformation from materials like stainless steel and copper. The Profile Bending Adapter PB20 enables the bending of flat steel bars, square steel, and round bars without difficulty. The Uniflex UBM 6-20 manual pipe bending machine offers a straightforward and economical solution for bending metal pipes. It accommodates pipes with wall thicknesses up to 2.5 mm and external diameters ranging from 6 to 20 mm. The machine's robust frame features a hexagon holder, allowing it to be securely fixed in any vise for stable operation. Its many adjustment options and telescopic arm enable the precise bending of strong pipes without causing out of roundness or corrugations. This design ensures that even thick-walled pipes can be bent effortlessly and accurately, making the UBM 6-20 a versatile and reliable tool for various pipe bending applications. The Ultimate Car Dismantling System is a highly efficient and environmentally friendly solution for processing end-of-life vehicles. It features a compartmental setup with 6 units, ensuring a structured and safe workflow. The continuous transport system moves cars seamlessly through the dismantling process, allowing for a high processing volume of 10,000 cars per year while maintaining low dismantling costs per vehicle. A key advantage of this system is the safe removal of hazardous substances, reducing environmental risks and ensuring compliance with new government policies. The design prioritizes a labor-friendly working environment, utilizing top-quality Dutch tools for precision and efficiency. The smart positioning of machinery enhances safety while enabling the recovery of at least 95% of materials, minimizing waste and maximizing resource reuse. By dismantling vehicles on a large scale, many reusable car parts are salvaged, and each car yields approximately 1,500 pounds of metal. The Ing Bonfiglioli Drake Metal Scrap and Car Shredder is a powerful and efficient machine designed to process metal waste. It operates through a series of rotating hammers that rapidly break down metal materials into smaller, manageable pieces. The system features an automatic feeding mechanism that guides scrap metal into the shredding chamber, where high-speed rotating drums and hammers apply intense impact and shear forces. Once shredded, the material passes through a series of screens that ensure uniform sizing before being discharged. The machine is fully automated and can be remotely monitored for real-time adjustments, ensuring optimal performance. Its compact design allows for easy installation without extensive foundation work, making it a simple, reliable, and affordable solution for metal recycling. Forging a gear blank begins with heating a metal billet to high temperatures and pressing it into shape using a forging press or hammer. This enhances the grain structure, improving strength and durability. The forged blank is then machined to precise dimensions before gear cutting. CNC gear hobbing is a precise process where a rotating hob cuts teeth into the gear blank. This method ensures high accuracy and efficiency, making it ideal for mass production. CNC control allows for complex geometries and tight tolerances. Mechanical gearbox production involves assembling multiple gears, shafts, and bearings into a housing. Precision machining ensures smooth operation, while heat treatment enhances wear resistance. Gearboxes are tested for performance and durability before deployment in automotive, industrial, and heavy machinery applications. HE VLC gear manufacturing line operates as a fully automated system utilizing the eMag Track motion automation system for seamless workpiece handling. The process begins with Opus 10, where the first side of the workpiece undergoes turning. Once completed, the workpiece is transferred to the next station for OP20, where the second side is turned to achieve the required dimensional accuracy. After turning, an optional post-process measuring system can be utilized to verify machining precision. The workpiece is then transferred via the translift system to the next machining stages, Opus 30 and OP40. In Opus 30, the gear undergoes hobbing, ensuring precise tooth cutting to meet design specifications. Following this, in OP40, chamfering is performed using a roller chamfering method, which smooths the gear edges to improve handling and assembly. Once machining is complete, the finished workpieces are marked for identification. A loading gantry then stacks the processed gears into standardized carrier baskets, ensuring efficient organization and transportation for subsequent operations. The Caltech full automatic ring rolling machine operates with a fully automated process, ensuring precision and efficiency. Once the start button is pressed, the machine executes all stages, approaching, rolling, and returning, without manual intervention. The intelligent control system adjusts rolling parameters for optimal forming, producing high-quality rings with consistent accuracy. Its smart automation minimizes errors and maximizes productivity, making it ideal for industrial applications. The rigid frame and advanced sensors ensure smooth operation, while high-performance rollers shape the material with precision, achieving perfect rings effortlessly. Two CNC-controlled ring rollers shape seamless rings from pre-forged blanks with precision. A computer-controlled process monitoring function provides real-time visual data on volume, dimensions, and out-of-roundness throughout the rolling process. Rolling parameters can be manually adjusted for optimization. The machine can produce rings from 10 kilograms to 8,000 kilograms, with diameters ranging from 250 millimeters to 3,500 millimeters and widths up to 850 millimeters. The process ensures minimal material waste, tight tolerances, and optimal mechanical properties for applications like gear wheels and bearings. France's turbine FUT machining involves precision manufacturing of the turbine's key components, such as the runner, guide vanes, and casing, to ensure efficiency in hydroelectric power generation. The process includes CNC milling, turning, and grinding to achieve tight tolerances and smooth surfaces for optimal water flow. Advanced 5-axis machining is commonly used for complex geometries, ensuring high accuracy. Surface finishing techniques like polishing and coating enhance durability and resistance to cavitation. Quality control with CMM inspections ensures the final product meets strict performance and reliability standards. This section is about machining of an aluminum engine block on the Hermle C30. Using a spindle speed of 18,000 revolutions per minute and 15 kilowatts power, the process begins with the clamping system, Gressel type GREPOS5X, securing the workpiece. The operation utilizes aerosol dry lubrication by Rother, minimizing coolant usage while enhancing tool life. The machining program, generated using Hypermill CAD CAM software, controls the cutting paths for optimal efficiency. Drilling operations. A VHM 90 degrees drill creates precise holes for mounting points, lubrication channels, and cooling passages. Thread forming. The InnoForm GLT8 thread former shapes internal threads without generating chips, improving thread strength. Face and pocket milling. Cut hem end mills perform high-speed roughing and finishing of surfaces, ensuring dimensional accuracy. Thread milling. The VHM Vario thread mill produces high-precision screw threads. Chamfering and contouring. A modular insert end mill with rhombic inserts refines edges and contours critical areas. This process ensures the aluminum engine block is precisely machined, maintaining tight tolerances and high-quality surface finishes. The production of a Boeing 777 landing gear housing begins with CAD preparation in Tebas software. The enormous forged steel blank undergoes precise machining to create a high-tech aerospace component with delicate structures. Digital work planning is carried out in Tebas, utilizing stored machining templates, tool libraries, and simulation capabilities to ensure a safe and efficient process. NC programming follows, where all machining sequences, tools, and cutting parameters are documented in the job manager for process control. The manufacturing process starts with roughing operations, using optimized short tools to remove excess material efficiently. Tebas material tracking ensures accurate re-roughing, preventing tool collisions and optimizing machining performance. The process transitions to 3+2 axis finishing, refining the component's geometry with high precision. Throughout the machining cycle, Tebas simulation validates each step by replicating the real-world manufacturing environment through digital twins. This guarantees process reliability, minimizes errors, and enhances machining quality. Injection molding machine screw processing on a CNC lathe involves precision machining to achieve the required dimensions and surface finish. The process starts with a metal blank, which is securely clamped in the lathe's chuck. The CNC lathe then uses various cutting tools to shape the screw, performing operations like turning, threading, and grooving. Special attention is given to the flight depth and pitch for efficient plastic melting and mixing. High-precision CNC control ensures consistency, and final polishing enhances wear resistance and longevity. Stranding, where multiple wires are twisted together to form strands. This process is performed using precision stranding machines to ensure uniformity. Once the strands are formed, they are further twisted around a core, either fiber or steel, to create the final wire rope structure. This step, known as closing, determines the rope's flexibility and load-bearing capacity. During production, various automated systems such as automatic measuring machines and automatic racks ensure consistent quality. Special devices like triangular vise are used for securing the rope during processing. For high-strength applications, the rope undergoes additional treatments such as pressing using 3,000-ton press machines and techniques like the Amsler vertical tester. Final cutting is performed using thermal cutting machines. The completed wire rope is tested for strength, flexibility, and durability before being used in lifting applications, including slinging and hand splicing and turntable mechanisms. The spring steel wire is heated to nearly 1,000 degrees Celsius in a walking beam gas furnace before being coiled on a CNC computer-controlled coiling machine. This hot coiling process ensures consistent results in the finished spring. After coiling, the spring is transferred to a quenching tank, where it is hardened for strength. The oil in the quenching tank is circulated and cooled to prevent hot spots on the coil's surface as it quenches. Next, the coil is moved by a conveyor chain into a tempering furnace, where it is tempered at over 400 degrees Celsius for about 20 minutes. This tempering process reduces brittleness and enhances elasticity. If required by the design, the coil ends are then ground flat on an automated grinding machine. The coils are then placed in a shot peener, where they are bombarded with hardened steel shot at high speed. This shot peening process relieves surface stress, making the wire more durable and less prone to fatigue, and leaves a clean, keyed surface for the final coating. The next step is scragging, where the coil is fully compressed to its solid height. This presetting process prevents sagging and height loss. The coil is then load height tested to ensure it meets the specified height and load requirements for that part number. Finally, the coils are powder coated for a durable, protective finish, then labeled and boxed for distribution. The coils undergo all these processes to ensure consistent height and rate, durability, and a quality surface finish. Tiger leaf springs undergo a rigorous testing regime that meets the high standards of car manufacturers. Among these tests is the crucial load test, which identifies the load classification to ensure the correct posture of the vehicle when installed. This load test is vital for verifying that all components of the Tiger leaf springs, including materials and base fixings, are fit for their intended task and loading conditions. By subjecting the leaf springs to this test, manufacturers ensure that they can withstand the stresses and demands of real-world use, providing reliability and safety for the vehicle. This comprehensive testing process guarantees that Tiger leaf springs deliver optimal performance and durability, maintaining the proper vehicle stance and handling under various load conditions. A truss roll forming line is a specialized production system used to manufacture roof truss channels efficiently. During the initial testing phase, short pieces are produced to evaluate the machine's performance in terms of length tolerance and cycle timing. This step ensures that the roll forming line can produce components with precise dimensions consistently, which is crucial for the structural integrity and fitment of the roof trusses. The system typically includes various stages such as decoiling, roll forming, cutting, and stacking. By automating these processes, the truss roll forming line enhances production speed, reduces material waste, and ensures uniformity in the final products, making it an essential tool in modern construction. Rolling a cone on a 3-roll bending machine is a precise and intricate process, depicted effectively in the video. The procedure begins by positioning the metal plate, which has been pre-cut into a specific trapezoidal shape, between the 3 rollers. The machine features 2 side rollers and 1 central top roller. The side rollers are adjusted to apply lateral pressure, while the top roller exerts downward force. The process starts with the top roller pressing down, initiating the bending of the plate into a conical shape. As the rollers move, the plate is gradually bent into a cone. Precision is key, as the rollers need to be adjusted to maintain a consistent and smooth curvature. During the bending of a concentrical reduction, the setup ensures the cone's large and small diameters are accurately formed, maintaining concentricity. The central top roller plays a crucial role in ensuring the cone's apex and base are properly aligned. This method is commonly used for creating components in various industries, such as pipelines, silos, and other structures requiring conical shapes. Rolling mills are integral components in the production of metal products, especially in the steel industry. They are designed to reduce the thickness of metal stock or to change its cross-sectional area through a series of rollers. The process involves heating the metal to a pliable state and then passing it through the rolling mill. There are various types of rolling mills, including hot rolling mills, cold rolling mills, and tandem rolling mills, each designed for specific applications and material types. One of the products processed in rolling mills is straight mill round material. This material is typically a cylindrical piece of metal, such as steel, that has been hot or cold rolled to a specific diameter and surface finish. Straight mill round material is used in a wide range of applications, including the production of shafts, bolts, and other mechanical components. The precise control over the diameter and surface finish of the round material makes it suitable for high-precision applications. Once the straight mill round material has been produced, it often undergoes further processing in a block mill. The block mill is a specialized type of rolling mill designed to handle the specific requirements of straight mill round material. The transition from the straight mill to the block mill is a critical step in ensuring the final product meets the necessary specifications. In this stage, the straight mill round material is carefully guided into the block mill. This transition involves precise alignment and control to ensure the material enters the block mill without any damage or deviation from the desired path. The process is usually automated, with sensors and control systems ensuring the material is correctly positioned and fed into the block mill. The block mill further processes the straight mill round material, refining its dimensions and surface finish. The block mill typically consists of a series of closely spaced rollers arranged in a sequence that progressively reduces the diameter of the material and improves its surface quality. The rollers in a block mill are designed to exert uniform pressure on the material, ensuring a consistent and high-quality finish. One of the key features of a block mill is its ability to produce round material with extremely tight dimensional tolerances. This is achieved through precise control of the rolling process, including the speed, pressure, and temperature of the rollers. The block mill also incorporates cooling systems to manage the temperature of the material and the rollers, preventing overheating and ensuring the material maintains its structural integrity. Integrated wire drawing, straightening, and cutting machines with a 2-drum 4-cassette system are highly specialized equipment designed to enhance the efficiency and quality of wire and rod production. These machines are capable of handling wire diameters ranging from 3 mm to 16 mm, with a remarkable maximum operational speed of 250 meters per minute. This combination of versatility and speed makes them invaluable in industries requiring precise and high-volume wire production. The integrated machine uses 2 drums in conjunction with 4 cassettes to ensure a continuous and smooth drawing process. The cassettes, which hold the drawing dies, are strategically placed to achieve the desired reduction in diameter while maintaining the structural integrity of the wire. Steel rods are often rolled into coils for easier handling and transport. However, these coils need to be straightened before they can be used in various applications. The integrated machine includes a straightening mechanism that ensures the wires or rods are perfectly straightened after being uncoiled. This is critical for applications where precision is paramount, such as in the manufacture of electronic components, automotive parts, and construction materials. The final stage in the process is cutting the wire or rod into equal lengths. The integrated machine's cutting system is designed to operate at high speeds, in tandem with the wire drawing process, to ensure that production efficiency is maximized. The cutting mechanism is engineered to provide clean, burr-free cuts, which is essential for maintaining the quality of the wire or rod and ensuring it is ready for immediate use or further processing. The integration of these processes into a single machine offers several advantages. It reduces the need for multiple pieces of equipment, thereby saving floor space and reducing capital investment. It also minimizes the handling of wire or rods between processes, which reduces the risk of damage and improves overall production efficiency. Moreover, the high-speed capability of the machine, combined with its ability to handle a wide range of wire diameters, makes it a versatile solution for various industrial applications. This cassette system roll forming line is a versatile and efficient production system used in the manufacturing of various metal profiles. The key features of this system include a total motor power of 30 kilowatts, a cassette change speed of up to 40 meters per minute, and an air requirement of 100 liters per minute at 6 bars. It is designed to handle sheet thicknesses ranging from 0.35 millimeters to 0.70 millimeters, with a production speed of 20 meters per minute. The machine requires only one operator and spans 28 meters in length and 6 meters in width. It can process materials such as galvanized steel, painted copper steel, and aluminum. The operation of a cassette system roll forming line begins with the feeding of metal sheets into the machine. These sheets are either pre-cut to the required length or continuously fed from a coil. The system is equipped with a destacking mechanism that ensures a smooth and consistent supply of sheets into the roll forming line. Once the sheet enters the line, it passes through a series of forming stations where the metal is gradually shaped into the desired profile. Each station is equipped with rollers that progressively bend the sheet, ensuring precise and consistent formation. The cassette system allows for quick and easy changeovers between different profiles, maximizing production efficiency. This is particularly useful when producing a variety of profiles on the same line. Throughout the forming process, double sheet control mechanisms are in place to prevent any misfeeds or overlaps, ensuring the quality of the final product. Additionally, edge preparation units clean and prepare the edges of the sheet, which is crucial for achieving clean and precise welds in subsequent processes. Expert Crane's production process begins with sourcing high-quality raw materials, which are brought into the facility for fabrication. The steel components are cut, welded, and machined to precise specifications. Overhead cranes, including bridge cranes, gantry cranes, and jib cranes, are assembled using advanced engineering techniques. The hoists and trolleys are integrated with the crane structure, ensuring optimal load handling and durability. Electrical control panels, both basic and intelligent versions, are installed and tested. Each crane undergoes rigorous quality checks, including load testing and operational assessments. Once approved, the completed cranes are shipped to customers. This complete brass forging line begins with a sawing machine, which cuts brass rods into precise billet sizes. The billets then move to the graphitizing station, where a thin layer of graphite is applied to reduce friction and prevent sticking during forging. Next, the billets enter the heating furnace, where they are heated to the optimal forging temperature. Once hot, they are transferred to the forging press, which shapes the brass billets under high pressure, forming the desired components. The Rotoline TQ50 machine is a fully automated oven machine designed for manufacturing large volume tanks with high efficiency and precision. The process begins with an automatic material weighing system, ensuring accuracy and agility without human intervention. The weighed material is then automatically fed into the mold, eliminating manual handling and improving process consistency. The oven cycle is initiated, utilizing state-of-the-art technology to heat the mold uniformly. This double cart system enhances productivity by allowing continuous operation. Once the heating phase is complete, the mold moves into the cooling cycle, ensuring controlled solidification and dimensional stability of the tank. An automated mold opening and closing system streamlines operations, reducing risks and improving efficiency. Upon cooling, the mold opens automatically, and the finished tank is removed. The next cycle starts immediately, with the mold closing and new material being fed in automatically. This automation results in higher safety, economy, control, repeatability, and quality. The process also optimizes cycle time, gas consumption, and mold maintenance, reducing operational costs. The TQ50 machine's easy-to-operate software ensures seamless operation with minimal human supervision. Designed for high-volume production, it enhances efficiency, reliability, and overall manufacturing performance. The assembly of a 270 megawatt steam turbine at Doosan Škoda Power in Kemi, Finland, represents a significant engineering and manufacturing achievement. The turbine is designed for high efficiency and reliability, ensuring optimal power generation for industrial and district heating applications. The project involves assembling a multi-stage, condensing-type steam turbine with an advanced control system for precise load adjustments. The turbine's high-pressure (HP) and low-pressure (LP) modules are key components, each weighing several dozen tons. The rotor, a crucial part of the assembly, undergoes precision machining and balancing to withstand rotational speeds of approximately 3,000 rpm. The generator coupling process ensures minimal vibration, enhancing operational stability. The turbine casing is assembled with a high degree of precision, requiring tolerances within 0.01 mm to ensure optimal steam flow efficiency. During installation, over 50 specialized engineers and technicians work on aligning the rotor, stator, and auxiliary systems. The entire assembly process takes approximately 6 months, including rigorous testing phases. Heat-resistant materials, such as chromium molybdenum steel, are used for high-stress components to endure steam temperatures of around 600 degrees Celsius. The emerald production process in southern Ethiopia begins with geological exploration to identify potential mining sites. Exploration drilling is conducted to locate emerald-bearing pegmatite formations and reaction zones where high-quality emeralds are found. Once a viable deposit is identified, test sampling is performed to evaluate the gem potential. Mining operations start with controlled blasting of pegmatite rock, followed by excavation to extract rough stones. The rock is then sorted, with workers manually selecting pieces that may contain emeralds. These selected stones are transported to processing facilities, where they are broken down further to expose the gems. Initial classification is done based on color intensity and transparency. High-quality emeralds are typically found in reaction zones, where beryllium from pegmatite interacts with chromium from the surrounding rocks. These emeralds have a richer green hue compared to those embedded in quartz and feldspar. Once extracted, the rough stones undergo preliminary cleaning and are sent for laboratory analysis to confirm their gemological characteristics. After grading, the stones are cut and polished to enhance their appearance. Finally, the processed emeralds enter the international gemstone market, where they are sold to jewelers and collectors. The growing mining industry in Ethiopia is rapidly positioning the country as an emerging player in the global emerald trade. Route's smart plywood manufacturing process integrates advanced automation and precision technologies for maximum efficiency and material utilization. The process begins with log conditioning, where logs are prepared for further processing. The log grading line ensures optimal raw material selection before entering the Route Smart Peeling line, which maximizes veneer recovery with Smart Scan HD technology. Auto calibration maintains continuous accuracy, while Meccano VCO machine vision enhances face veneer recovery and clipping precision. The drying line, equipped with Meccano G5 drying solutions, ensures superior grading accuracy for all wood species, optimizing moisture levels for further processing. The face veneer stacking system categorizes veneers by moisture content, enhancing material efficiency. Veneer value optimization employs real-time simulation for patching, core veneer composing, and face veneer composing to enhance material usage. The process includes scarf jointing, core veneer composing lines, and face veneer composing lines, increasing the amount of high-quality face veneer. The P2 patching line further upgrades veneer quality with cost-saving one-side gluing technology. The final stages involve pre-pressing, automatic pressing, and trim saw line operations, ensuring high panel value and overlaying for premium finish. The core mattress production industry processes over 900,000 metric tons of coconut husks annually, primarily in India, Sri Lanka, and Thailand. Core fibers, extracted from husks, are needle punched and bonded with latex, 10–20%, ensuring durability. Mattresses typically have a density of 60 to 120 kilograms per cubic meter and thicknesses ranging from 4 to 10 inches. The global core mattress market, valued at $1.5 billion, is growing at 5.8% CAGR, driven by eco-friendly demand and orthopedic benefits. It involves pouring molten aluminum, often from recycled cans, into abandoned fire ant colonies. The aluminum fills the tunnels, creating intricate sculptures once cooled and excavated. This process highlights the ants' complex architecture while recycling aluminum waste. Friction stir welding allows joining aluminum without melting, using a rotating tool to forge materials together. Traditionally slow for automotive use, advancements at Pacific Northwest National Laboratory increased speeds to over 3 meters per minute, enabling high-volume aluminum component production. The fully automatic Caltech ring rolling machine from South Korea handles the entire rolling process, approaching, rolling, and return, automatically. With a simple click of the start button, it produces precise, high-quality rings efficiently and reliably. The copper rod upcasting machine produces copper rods from Millbury copper wire scrap through melting, casting, and rolling processes. It handles both copper scrap and cathodes, offering a yearly production capacity of 3,000 to 12,000 tons efficiently and reliably. Getai Hydropower specializes in advanced hydro turbine manufacturing, focusing on precision engineering and high-performance components. The nozzle assembly plays a critical role in regulating water flow to the turbine, optimizing energy conversion efficiency. The CM4005 Axis Beam Mobile Gantry Machining Center is used for CNC machining of impact runners, ensuring precise and durable components for enhanced turbine performance. The assembly of the Francis turbine water guide mechanism involves integrating guide vanes and control systems to direct water flow efficiently, improving operational stability and energy output.